Every wire on Earth loses energy. Always, everywhere, unless it is a superconductor. That global loss adds up to 2,500 terawatt-hours wasted as heat every single year. The only known escape from this waste was discovered in 1911 when zero electrical resistance was observed at just 4 Kelvin. Zero resistance means a current flows forever using no energy. But perfect conductivity is only half the miracle. Superconductors also expel all magnetic fields, resulting in perfect, frictionless levitation. This happens because resistance normally comes from electrons scattering off thermally vibrating atoms in the lattice. Cool the material below its critical temperature, however, and resistance becomes exactly zero. Not almost zero, exactly zero. At that transition, the entire material condenses into a single macroscopic quantum object. The mechanism: one electron distorts the lattice, attracting a second electron, and a Cooper pair is born. BC's theory explained this pairing completely until 1986, when the discovery of cuprates shattered the known limits. Cuprates broke the temperature ceiling dramatically, yet their pairing mechanism, after decades, remains unsolved. That cuprate pairing mechanism, after 40 years of intense research, remains one of physics' deepest mysteries. And yet, YIBCO, a cuprate superconducting at 93 Kelvin, is already commercially used in power systems. No theory predicted cuprates, and no theory now predicts where a room temperature superconductor will finally be found. But the search is getting closer. The current record stands at 250 Kelvin, just 43 degrees below room temperature. Alongside that search, we've already harnessed flux-pinning quantum locking that anchors a levitating magnet in mid-air. Each pinned magnetic vortex contains exactly one quantum of magnetic flux. Not more, not less. 1. Type 2 superconductors accommodate these vortices, allowing them to stay superconducting even under extreme magnetic fields. Across the whole sample, all Cooper pairs share the same quantum phase, turning the material into a single coherent quantum object. This phase coherence enables Josephson junctions, the core of SQUID's the most sensitive magnetic sensors ever built. Even clinical MRI magnets exploit persistent supercurrents, meaning their huge fields require no ongoing electrical power. The Large Hadron Collider demonstrates this at scale, using 7,600 tons of superconducting wire. But above the critical temperature in cuprates, the pseudogap phase appears another unexplained state that has puzzled physicists for decades. These exotic quantum behaviors exceed what classical computers can model. We built quantum computers precisely to simulate such systems. That quantum-assisted search has now expanded to nicolates, discovered in 2019, the newest class of high-temperature candidates. Recently, LK99 was claimed as a room-temperature superconductor. Hundreds of labs worldwide raced to replicate it. LK99 failed to reproduce, but the global scientific community verified this within weeks. The system works, and it worked fast. The economic prize driving this urgency is enormous. Superconducting power grids in the US alone would save $20 billion annually. And such a material would enable maglev trains without any cryogenic cooling, removing the last barrier to widespread adoption. Fusion reactors, too, depend on powerful superconducting magnets, a prerequisite for delivering practical fusion energy to the grid. Thus, a single material discovery could simultaneously transform global energy, transportation, and even medical technology. Beyond ordinary superconductors, topological superconductors may host Majorana modes, quantum states that are protected by the material's very shape. To accelerate the search, AI now screens thousands of candidate materials per day, a rate impossible for humans. When a genuine room temperature superconductor is found, it will be confirmed by independent labs worldwide within weeks. Instantly, in historical terms. That confirmation wouldn't just improve existing technology, it would rewrite the fundamental rules of civilization. Even the search itself has already transformed society, giving us Curie, maglev, and the quantum computing revolution. So I ask, what would you do with a room temperature superconductor? Tell me in the comments. Just consider the climate impact: 600 million tons of CO avoided each year through physics alone. Room temperature superconductors would also dramatically simplify quantum computing from millikelvin to a relatively mild 4 Kelvin. Current estimates place a 60% probability of discovering a room temperature superconductor by 2040. Because the simple, stubborn fact remains, every wire loses energy, but the physics says it absolutely doesn't have to. Picture this: superconductivity in a material just sitting at room temperature. No cooling, no power loss, just physics, made real. If that vision excites you, subscribe to NexaVision. Every Wednesday we explore the technologies building tomorrow. If this changed how you look at every wire on Earth, hit the like button, it truly helps. Next on NexaVision, carbon nanotubes and graphene, the materials that will take us beyond silicon. The search for this transformative material spans hundreds of laboratories on 6 continents, all working in parallel. 4 major material classes, cuprates, hydrides, nickelates, and others, are currently locked in the race for the room temperature prize. However, predicting a promising material is only half the battle. Synthesizing it perfectly is the other, equally difficult half. Confirming a true superconductor also demands multiple independent measurements, zero resistance, the Meissner effect, and spectroscopic proof. We know the problem. We know the physics. We just need to find the right arrangement of atoms. That search is well underway, and when it succeeds, it will change the world. Thank you for exploring one of science's greatest open questions with NexaVision. The future is closer than it looks.